So let's start another problem that's related to the box that slides down an inclined plane. So the box has mass of 2 kilograms and it's attached by a rope or a string to a spring. And the spring constant is given as 120 newtons per meter. So the question is, what is the speed of the box after it slides down 10 centimeters down the incline? So that's the question. So there are a few things that we need to assume. So one thing that we need to assume is that there is no friction on the inclined plane. The pulley itself here is massless and frictionless. Okay. So, so a few more things that we need to take into account. So whatever distance this box slides down by, okay, is the distance by which the spring stretches. So if the spring stretches by 5 centimeters, the box slides down by 5 centimeters. So that's fairly obvious, right? Now, if we look carefully at the free body diagram here, and if this is the mass that represents the box, then it has a tension force that's pulling it back up. And this tension force is acting this way, right? And it comes from the tension of the spring. So this tension force equals K times the extension of the spring. So the downwards force here is the gravitational force, that is resolved along the direction of motion. So it is mg sine theta. Right? So here, to answer this question, what's the speed of the box after it slides down 10 centimeters down the incline? Okay, we use the work-energy theorem. So the work done on the box is the change in its kinetic energy. So if we look at the net force, on the box, okay, the net force on the box is the force of gravity resolved along the inclined plane minus the resistance of the spring, that is kx. So if the block were to slide down by distance dx, then this would be the amount of work that would be done, okay, and that would equal F net times dx. So F net here is the net force is mg sine theta minus kx. To find the net work or the total work, we integrate F net times dx, right, from the initial configuration where the block hasn't moved at all to where it has moved by 0.1 meters. So it is mg sine theta minus kx dx integrated between 0 and L. So if you carry through this integration, this comes to mg sine theta L minus half kl squared. Right. So that's the total work done here on the box. So if you look at the change in the kinetic energy, to begin with, the box is at rest, and this is its kinetic energy after it has slid down by distance of 10 centimeters. So the change in kinetic energy is half mv square minus 0, that is half mv square. So here v is the quantity that we need to determine. So once you've forgotten about the 0, what we can do is we can rearrange this equation right here into this form, and then substitute in the values of g equals 9.8, L is 10 centimeters, that is 0.1 meters, theta is 40 degrees, K is 120 Newton per meter, M is 2 kilograms, and L is 0.1, so that's 0.1 square. So we come up with a velocity of 0.81 meters per second, right? That's purely using the work energy theorem. So I hope this helps you to conceptualize how to solve these kinds of problems in future.